Okay, first thank you the organizer for giving me the opportunity for this talk. So today I am going to talk about this asymptotic properties of volatility estimator from high frequency data modeled by mixed fractional Brownian motion. So before going to the main problem, first I will explain step by step what are these terms in the title. First, what is mixed fractional Brownian motion. Then we are going to say what is high frequency data. Then we are going to see that what is the volatility. Next thing is what is its estimator, and final step is what is its asymptotic properties.
So you're going backwards.
Yeah. So first we say that what is this mixed fractional Brownian motion. So this mixed fractional Brownian motions, by that I mean this is simply linear combinations of a Brownian motions and a fractional Brownian motion for our setup with, and they belong to the same probability space and complete probability space. They are two independent process, and well, Brownian motions probably everybody knows here. So for fractional Brownian motions, we want to say that fractional Brownian motion is a Gaussian process, centered Gaussian process, where Brownian motions have independent increment. Their fractional Brownian motions do not have independent increment. So increment process actually correlated. So that's the main difference, and this correlation is controlled by one parameter. It is called Hurst parameter and denoted by h here, and this h is the range in 0 to 1. Now, depending upon these values of h, fractional Brownian motions behaves differently. If this value of h is less than half, then we call the fractional Brownian motion shows a short memory process. By that means we have this incremental process covariance, sum of the covariance is finite. Whereas for h greater than half, for the fractional Brownian motions, the covariance structure, this incremental process covariance structure, if we sum it up, then it is going to be infinite. So we call it long memory process. So this is the two difference between h less than and greater than equals to half. So I have here just giving that what is the combinations of this Brownian and fractional Brownian motions, that mixed fractional Brownian, what are the moments directly. So you can see that moment is, both are centered, so moment is actually adds up, so 0. Covariance structure, because of independent, only adds up to the variance term, so variance of this Brownian motion terms and this fractional Brownian motion covariance, this is with the original process, not the increment process. And it just sum up, because it is independent, there is no covariance term between Brownian and fractional Brownian motions. And then there is this things, if I denote this process by with this alpha beta like this, then this says that it is scaled in such a fashion that the distributions will be what we call as self-similar. So if you, that simply means that this small h is actually scaled about this alpha. Well, so if you just scale it, then we get the distribution. So we are going to see these properties later. So this is a simple self-similarity property, and throughout our talk, if otherwise not mentioned, this alpha or beta is to be taken to be 1. Now what is this nice things about fractional Brownian motions, why one at all will come to consider these things. Now there is a paper by Cheridito which actually shows that this Brownian motions is actually having very nice properties. So in case of stochastic integration theory. Now, but Brownian motions have, from practical point of view, is lacking a property that is, it has independent increment process. Now when people tries to use the Brownian motion to model, in specifically case of finance modeling, then what they do not want that process to be independent increment, because if yesterday's to today's there is an increment in the stock price, then they do not expect that from today to tomorrow, whether it will be increment or whether it will going down, it will be totally independent. So because of Brownian motions have this independent increment structure, so they don't want these to use in modeling stock price. We will going to see the model. So So they just want to improve this instead of Brownian motions if they want to get something nice. So they just directly try to take this fractional Brownian motions, because these fractional Brownian motions have certain have a dependent increment structure. But being a dependent increment structure, it has certain other consequence we will going to see later. So now I am going to say this Cheretos result. It says that okay, this mixed fractional Brownian motions does not qualify to be even weak semi-martingale. I am not going to define that term, which simply says it is not even a nice process to be qualified to be a stochastic integration process. To qualify to be a nice stochastic integration process, Ito integration, if this process is semi-martingale, this is nice. But if it is not nice, then we are in trouble. So what he has shown that okay, for this interval, now I want to say one thing, that at half this process will to becomes a Brownian motion. So with this interval 0 to 3/4, this mixed fractional Brownian motion doesn't satisfy to be a nice property, having nice properties to qualify it. But for 3/4 to 1, at least MFBM is a semi-martingale. Now what the extra gain we are going to get? We are going to getting a semi-martingale which actually have a dependent structure, allowing a dependent structure. So that's one of the things, but it is a semi-martingale, and yes, it is equivalent to Brownian motions. By equivalence of two processes are equivalent, by that means their corresponding measures are equivalent, means they are absolutely continuous to each other. So this is this Cheretos result about just mixed fractional Brownian motions. And what he has also shown that if we take the quadratic variation process of the mixed fractional Brownian motion, by that means what he has means is, if you have time scale say 0 to 1, you chopped the time scale is T1, T2, Tn, and grid point is going smaller and smaller. So if you increase the n, there are more and more time point, and time point will be in this interval itself. So in this scenario, and you have observed the process like this, then what you will do, you just take this type of differences. This is the quadratic variation terms. If h is less than half, then this quadratic variation process up to fixed time is actually is infinity. And if this h is Haas parameter is greater than half, then this quadratic variation process is finite, and finite in probability limit. No probability limit. Yes, this is a stochastic quantity, so it's going to probability to this finite and infinite. Now here at this point I want to mention this thing. When we are taking this data point, here what we are doing, actually we fix a time point and chop it up and taking the data. So in later slides I will going to consider that as a high frequency data. In statistics, if I can take a data which is looking like 0 and keeping an interval length h fixed, and then take h, 2h like that and increase the data, then we will not call this normal frequency, means ordinary collecting of data. Now this way of collecting data is not the same as this way of collecting data. Here in the whole analysis, this h is going to get fixed. So usual way of discretizing the data. Now here is the discretization of the data is different by that sense. So this is what we are going to say high frequency data. So what Cheretos work actually says is, it talks about this quadratic variation process, how it is behaving with the fact that how h is behaving. That's all it says, and it talks about the probability limit. Now what is our model? Now next comes to this fractional Brownian motion driven model, which will be used for stochastic stock price modeling. Now look at this equation. This equation is actually looking like, if you know about this Black-Scholes kind of equations, which is basically solutions of Black-Scholes equation, which is basically geometric Brownian motions, it is looking like analog of this geometric Brownian motions. So this exponential things actually making this writing this thing solutions as a positive solutions. You want, if you remember the Black-Scholes equations, the solutions you get, if you just try to model it only by Brownian motions or its linear combinations, you get positive and negative everything. So if you just make it exponential, you will get only positive things. Stock price is always positive, so better you model something which is positive. So this is kind of analog of this geometric Brownian motions, of this geometric fractional Brownian motion. Now here I will not going to do the details, but I can say little literature that what is existing. So when people have actually come up with geometric Brownian motions, they actually come through this Black-Scholes model. So you may ask that there may be corresponding a stochastic differential equations corresponding to mixed fractional Brownian motions, and this may comes as a solutions of that stochastic differential equations. Yes, there are many different notions of integrations to do the integrations with respect to mixed fractional Brownian motions, because I say that mixed fractional Brownian motions doesn't qualify to be straight way to this Ito integration sense. So there are different notions of integrations and they come up with, but I am not going to do these things because they actually need a lot of loopholes to fix up. So what I am taking this model directly from a physics paper where they actually using this model to describe a stock price or some future or forward market, so that this is now free from any ambiguity and kind of thing. And so this kind of model is as their own is making sense, so there is no problem with it. Now for our purpose, we can see that why we have setting this mu equals to 0, because if we do not set mu equals to 0, this is the drift term. In a fixed time, we cannot actually quite do well with this mixed term. So basically in fractional or whatever this Black-Scholes kind of setup, people actually use Girsanov and get rid of it, and then this kind of setup is helpful. So we are actually get rid of mu so that this kind of setup is helpful. In this setup there is no problem, estimation of mean, but in this setup there will be problem. So we actually get rid of this mu term. So we just want to set the mu term less equals to 0. So I just want to show you one picture of geometric mixed fractional Brownian motions, how it looks like, and what I have started with the motivations, that it keeps track of dependent structure, how it is going. Just want to see some graphs. So I have just plotted for h equals to 0.77 zone. Just recall that this is the zone where from I have picked up the h. This is the long memory zone, and I just want a rough sketch for a typical paths of mixed fractional Brownian motions, or maybe which is actually influenced by fractional Brownian motion is this. So if h less than half, then paths are like too many ups and down. If h greater than half, a typical path will have lesser ups and down, and if h greater than half, then paths are like even more smoother, as if more smoother path. So what happens, this quadratic variations, if you look back to this Cheredito's result, then more h is great, you are getting actually quadratic variations finite, whereas if you have a lot of zigzag, jittery, then actually you get quadratic variation is actually infinite. So this is one plot, and actually we have started doing things on practical things. So this is just Yahoo data from finance data, that S&P 500, and we try to fit these models. But this having decided over this model of this kind is never a kind of confident job that, well, okay, one can fit a model, but that never says a lot of things. So mainly I will going to see the theoretical properties, showing the simulations, how it is work, and what are the consequence. And if one wants to do the model, of course that part is open. So what we want basically, given this fractional Brownian mixed fractional Brownian data set, so we will going to set this kind of scenario, fixed time span, and we will get the data coarser and coarser data, and target quantity is, this is our target quantity, this sigma, this variance, and this variance quantity is target quantity. Usually in finance literature people call it volatility. So how to get the volatility? So basically somehow this quadratic variation terms will be an estimator of the volatility. And at this time point I want to emphasis on these things, that when we see these fluctuations of this paths of the mixed fractional Brownian motions, the variability actually jointly controlled by sigma and h both. Okay, so this variability, like the thing is that if I have some h from the given data, if I have one h and one sigma, and if you have some another h and another sigma, if I just manage it to change it, so there may be some identifiability problem. So that's one of the part, because the variability depend intricately on both. So if you just especially for those values which are nearly half values, greater than or less than half, and if you just modulate the sigma a little bit from the given data, it is difficult to judge whether which zone it is actually coming. And this zone coming thing is crucial because it determines whether the process is long memory or short memory. Okay, so we are interested in realized volatility with lot of pros and cons in that can happen, and we want to study these properties. Now I have already told that this data is like this coarser partition. Now I will going to say that why this coarser partition actually taken, means why not like this kind of partitions. I have said that fixed time interval partitions, so I have not taken that thing. That's because of the following reason. When people tries to use the stock price modeling, they typically tries to calculate what they call option price, and option price is typically European option call price have a fixed terminal time point value. So there is no point to getting the data point after a certain time. So their maturity time T for European call option price is fixed, some T. So if I want to get some estimator of option price, I have to get data whatever way I can manage the data up to the time T. There is no point of taking the data, lot of data which is actually getting out of this time zone. That's one thing. And secondly, in whole of our analysis, we actually fix the time point interval between 0 and 1, not from any 0 to arbitrary t, but that doesn't matter because this mixed fractional Brownian motion has a self-similar property. So because of this self-similar property, you always scale down this time t scale to time 1 scale. That's also possible. So we have this scenario, we have chopped off the interval, and small intervals we have the data. Now what we have going to say that what will be the suitable estimator. So this is the form of suitable estimator. You just take the log square because you just don't want the exponential to come down, and taking the square. Only interesting part is this normalizing constant. Now next slide, let us see. So this normalizing factor is coming out. It's nice way. If h greater than half, this normalizing factor actually going to 1. As if you do not need the normalizing factor for large n. And if is age less than half, then normalizing factor is actually acting. Okay, and now people are usually interested in the long memory process, not in the short memory process. So they are, because Cheredito's result says that for age greater than 3/4 it is equivalent to Brownian motions. So people are using mixed fractional Brownian motions in this regime of age mostly, and in this regime basically age greater than half regime where actually normalizing factor converges to 1. So, well, now having said this, I will say that though people have used a model for this regime, but for our case we can provide the asymptotic normality result for whole range of age, that means from 0 to 1. We can do the analysis for a whole range of age, and that includes this 3/4 to 1. Now before going to do that, we have seen that there is another estimator proposed by Sun. It's in a Physica A paper. So they actually have trying to use this fractional Brownian motion model. Their time point at T1 and T2, and their partition points are like T1, T2 kind of Tn, T0, and the partition point is such that it is getting smaller and smaller with no particular set of partitions. It is not like that refinement of the earlier partitions. The sequence of partition is not like that. Only constant is mesh size must be going to 0, and they have proposed this estimator, but they have not proved anything. They just say that it seems that this estimator, so there are things as if this estimator, I called it whatever, sigma curl or something, it behaves like this. So this is the result. There is no result for that how it is going to behave like this. So no rigorous proof for this result. So what we have done, in our case the partition point is not like any partition point. It is equal interval time point, partition point. So firstly our time point partition is if kind of typical time Ti and Tj is kind of, if I have n number of partition, so it is j by n and j plus 1 by n type of partition for our case, for whole range of age. And our case, this final and starting and end time point is fixed, 0 to 1. And if I have chosen, then these two estimators actually have this kind of linked with this kind of relationship. So what they have done, they actually consider the estimator for age greater than 3/4. So even if exact expressions need this involvement of normalizing factor which involve age, they actually roughly says that okay, you just don't need any normalizing factor. So that normalizing factor extra is popping up in our estimator. For age greater than 3/4, this normalizing factor again approximately equals to 1 in long term. So it is not exact for their case. So what are the properties we are going to show and we have proved? So first thing is, the way we construct this estimator, this is converges almost surely to the sigma square. This is the result one. Secondly, the way we construct this estimator, this is asymptotically distributed, normal distributed, and by chance this variance thing is very nice, simple constant, clean simple constant. And thirdly, that how the distributions, this is the bulk distributions of this estimator, this is the standard normal cumulative density. So how the bulk distributions of this probabilities and normal density deviate at what rate, this goes like this. So this is simply the variation bound, variation kind of bound, so bulk. Okay. Maybe I will just show you the simulation and this what are the problems and what we want to going to test, and then come back to the calculation. So main idea of this proof actually taken from this works of Noaillat, Pecati, Nudin, and it involves the multiple stochastic integration, Wiener chaos. This concept is used. It has been used the Madhava calculus as well as some fourth moment theorem. So there are some 2-3 very heavy toolbox is directly has been used to get this straightforward result. Simplified because it's just straightforward calculations of these things. But I will come this part later if I have time permits. And yes, for this variation kind of bound, what is this tool has been used that they somehow going to calculate. I'm just giving the brief idea that original if I able to write this estimator, my estimator like this Fn, then it talks about how the proof involves how Fn and somehow distributions of Fn and its normal distribution difference, if I write in suitable form, these two quantities correlation going to say something about this variation bound. So this is the very rough idea. But I can come back if time permits. So we just try to see that how actually the simulations method really works. So simulations method, because we have tried it for whole range of age, so we have given this whole range of age and just try to see that how this main thing works. So you can see that, well, this sigma square, if I take I have taken different sigma square values and just try to see that how it is working. So it is working fine, though we need more variance analysis. So even the properties of the estimator of variance of this variance estimator, that will be better. But till now we do not have this result. We only have the mean estimator and its corresponding thing. So we have these results are fine actually. So at least up to this mark, this theory and practical things matching, and this mean is close for all the values of age. Now, average over sample paths. Okay, so this is 200 sample paths. This is average over sample paths, and this chopping of things actually have 1000 chopping up. So one can actually play with this chopping up. So this part is coming more or less correct, unless otherwise how close is the close. If you just do not do the variance next level analysis, it will not be quite clear. That next part, what I am trying to do, or what is interesting, that I say that for age greater than half case, what is happening, that I say normalizing constant is actually going to 1 in long range. So the point is, if I somehow drop the normalizing constant, because now there is an interesting feature, this is the problem. See, I can from the data directly get these values, but if I need to use the normalizing constant, I need to know the age in prior, which from the data I do not have. So I need to get that age prior estimation and then incorporate it to that. So people, as they use this thing for long range data analysis, so they definitely will search for which age they will going to use. So if I know that for age greater than half, this normalizing constant actually going to 1, and I can drop it, then it will be better, because in the estimator procedure I do not have any involvement of parameter. I will get free from it. So we have tried it for age greater than half, how this simulation study is coming, and as expected, that as it's going to closer to, means, or I should not say expected, closer to the extreme long memory side, it's not closer to half, it's far away from half, they are still nice, but as it is coming closer to half, it is really behaving bad. So there is a problem near half, this identification problem, and if the variance is higher than near half, it is really going far. So that is actually a problematic part. So just dropping a normalizing factor if one can get some large deviation kind of setup so that they can get how is deviating, so that will be interesting, because then one can actually try to drop it, because what the analysis is actually about that bulk analysis, it's not telling about. So this is one part, and of course this age thing, so as a whole want to check for near half zone, so that how this normality convergence is happening and what is happening if it is going this outside the any large deviation kind of things, if it can be done. So well, so now I have some time, so maybe I can go to the rough sketch of proof. So this rough sketch of proof goes as follows. So all these techniques and tools and borrowed. So it talks about, first we will going to convert this our original process, Gaussian process. In our case it is mixed fractional Brownian motion. We first, our original mixed fractional Brownian motions is actually indexed by a time t. So R indexed process. So first step is we change it to a Hilbert space valued object. So what is, we called it isonormal Gaussian process. So what is this thing? We have taken this covariance structure, and with this covariance structure, it's the inner product we take in it. We have taken this indicator functions, and then we just calculate the covariance structure. Now this indicator functions of its span we have taken, is the standard recipe, and then end up with a Hilbert space, where this process is actually indexed by the element of this Hilbert space. Now for Brownian motion case, this Hilbert space turns out to be the C01, means function space. For fractional Brownian motion, it turns out to be distribution space, and for mixed fractional Brownian motion, its space is not nice function space, it's not, it is distribution space. So that's no needed, because we just work with the age. Next thing, so we have indexed the process first. Then next part is what we are going to see. We want to write our this thing as a what we call multiple stochastic Wiener-Ito integral. Whatever these things we are going to get. So what is this multiple Wiener integral? This is a map from these two spaces. This is a map from these two spaces, where H, you know, this is symmetric tensor product, you know, and it has a norm. And what is Wn? Wn is, you take the next slide, I will go, no. Yeah, so Ws is here. So what we are going to do, you consider the Hermite polynomials of order n, and you now your Hilbert space valued process, right? Previously it was MT kind of thing, now it is M5 of kind of things. You construct Hermite polynomial of these things. Take span, take closure, nth Hermite, for nth Hermite polynomial things, whatever object you will end up with, that is your Wn space. So In is the map from this thing. Okay, now next step, one able to show that our sigma hat square actually can be expressed in terms of this multiple Wiener-Ito calculus, if I make this map like this. Well, then what is the benefit? The benefit is actually we are going to use very strong theorems here to prove almost sure convergence. We actually can use a hypercontractivity property. Basically, almost sure convergence means we will use some kind of Markov kind of inequality, and will have an expectation on the right hand side, and that expectations will contracting in whatever way we want. So that's hypercontractivity property. Roughly speaking, we will going to use that thing to prove asymptotic almost show convergence. Next thing is, so we have being very heavy tools here. So to facilitate the proving the asymptotic normality. So there is, so this slide is saying that how our Fn, our estimator structure can be written in terms of this Fn. And there are several terms involved, but only one term is important, which can be expressed as I2 or IN kind of things, and rest actually one can manage with Slutsky or something. This part will going to be convergence in distribution, rest part will be going to be convergence in probability, convergence is pointwise convergence. So we actually basket up everything in the under Slutsky's theorem, and so only one terms is nice. And what is this thing? If this next step is actually showing that how I2 can be actually written in terms of I1 kind of scenario. So this whole business is actually, this is a recursive thing. This, if you have I1 and I2 two things, so they can be written in terms of others, so that we can get F as an expansion of this kind. So we just want an expansions. So this formula actually says that if we have different INs, how these INs are related. And after the end, at the bottom line, we just want a linear combinations of IN as these quantities. We just want this structure so that we can use apply the theorem, that's all. If I can do it, then I am not defining what is Malevich derivative. So if my functions looks like this linear combinations of these i's, whatever this basket is, then this Malevich derivative can be expressed in this form, which is needed only for the calculation purpose. Now, having said this, now we will going to use very strong result, this fourth moment theorem. This fourth moment theorem say that if one wants to show a asymptotic normality result, it is either shows this fourth moment because of this second condition, either you can show that you just somehow calculate these expectations. There is a way to calculate of this to the power fourth moment in terms of INs, and there is a way to calculate the expectations of INs. So just calculate it, show is going to 3. We have not taken that part. We have taken the fourth part, showing that Malevich derivative, whatever you want to show, that is going to n, where your original thing is that Fn, whatever order of n. If you can show it is in L2, then actually you are through with your proving with your asymptotic normality. So what we are going to do, for this case we just identify this quantity, we get this part and prove it. Show that this is converges to whatever the n is turns out to be in L2, and then the proof is finished. And I have probably no need to say this because this record any again things. Only thing is that you have original things and its distributions, difference, correlations. If you have get hold of that quantity somehow, then you actually are through these correlations actually going to give you this difference, how this difference is converging to this constant, to calculating the constant. So you have basically calculating the two-dimensional two quantities, which is Gaussian at the end, which have the second moment 1 and a correlations, and you just wanted to get the correlation because you just want this thing, and you end up this normalizing factor just to get the normalizing factor. So if you just put it, plug it back, then you are going to get it. So you will get asymptotic normality result. Yes, so that's all what I want to say. That so the thing is that it is high frequency data. We try to go this estimator, and we can show the central limit theorem, which is a bulk properties, but there are other unresolved issues like how this age is different values of age. Basically, problem is if you have two different age, ones have some distributions, other is corresponding give to another sigma distributions, right? And this sigma distribution may superimpose. So if one tails is another bulk, or another tails is another bulk kind of thing, because the variability actually messed up. So two different kind of distribution. So that's one to capture. And other than that, we got this variation bound and asymptotic normality, and it's theoretically up to this part it holds. And if you want to use this thing to the practical model, welcome, but anyways, it's always uncertain. So here are this reference. So one is very interesting reference by Cheridito, which is doing this mixed fractional Brownian motions, and this whole huge literature is actually I forget to mention Tudur. So a very good literature doing this thing. And in fact, for fractional Brownian motion, directly fractional Brownian motion, no geometry, nothing. So Tudur actually have shown this. So they have done this kind of analysis to other Gaussian process also. So particular in this setup and this normalizing, setting up normalization, that's the only part that we are trying to do, and maybe with the finance practice. That's. Thank you for your attention.
Yes, actually, I have a quite basic question concerning one of the first results that you quoted. I think this result by Cheridito. I'm not sure I understood really what it is, but so I understand the following. So you have this mixed fractional Brownian motion, which is the sum of Brownian motion plus fractional Brownian motion of first index h.
Yes.
Right. Now you say that if I understood it, that one of the theorem by this Cheridito is that if h is in 3/4 1, then the process is equivalent to Brownian motion.
Yes.
Okay, but then there's something I just don't understand. I mean, because naively, I mean, I don't know, if you look at your process on a finite interval, say up to time t, okay, I mean, the Brownian motion scales like t to the 1/2.
Yes.
And then the fractional Brownian motion stays like t to the h.
Yes, yes.
So for h between 3/4 and 1,
okay.
I mean, obviously, I mean, it's clear that it should scale like.
Okay. Yes. These two distributions are different. What Cheridito means is equivalence. Equivalence means the two measures as equivalence. If one on a null set giving nulls measures on a set giving 0, that implies other also that set giving 0. Absolutely continuous. If other is this one is giving 0, that is so that for that matter two measures do not have to be the same thing. So this is the equivalence conditions. It's
continuity is different, so then you get singularity.
Yeah, exactly.
Holder continuity is different, yes.
I mean, one is living on parts of holder half, another on holder something else. Weak semi-martingale.
Okay, weak semi-martingale. Well, it is so rough means I will say it later, but you consider the partition functions. So it talks about weak semi-martingale, some L0 kind of bound of this partitions, whole class of partition functions, but this is no way closer to practicality. I can say it. So, sorry.
I also had a similar question, like naively for very large t. So one would expect that it's just dominated by maximum of h½ right? Like whichever is larger.
For large t?
When t is very large, this whole process will be dominated by either h or half, whichever is larger, right?
What do you mean by dominated by? I'm not getting clear.
If I look at the distribution or something at a very large time,
okay.
It will either scale like t if h is less than half, or scales like t to the power h if h is greater than half, right?
Yes. So okay.
So then, if h is greater than half, at a very large time, it will be very different from a Brownian motion, I guess, right? It will be like a fractional.
In your sense, it's not equivalent in your sense.
No, equivalent for mathematicians is absolute continuity. It's not equivalent in the same process.
Maybe.
What was the logic behind the estimator for sigma square? You had
Oh, logic. Oh, this is, well, if you just try to do the maximum likelihood kind of estimator, okay, maybe I'll just look at this model. Okay. Look at this model. Basically doing nothing, just taking the log, so we get rid of exponential, and then you take the difference. So basically, after getting the difference, you will going to get the difference of Brownian motions, increment process, and some extra garbage term of times. Okay. Now the thing is that Brownian motion difference, then take the whole square. So something process, some extra garbage term, whole square, going to give the process whole square, some process into garbage plus garbage whole square. Now this garbage terms is a time things, so it is free from any, what is this thing, any stochastic process. So it is with a suitable normalizing constant, it will go to 0 pointwise. Process into garbage term, whatever it is, that is also not very difficult because it is mean zero process, centered process. You can probability or anyway get rid of it. Only thing is end up with your this process square term, and the process square term is this thing.
So my kind of question is whether if these logs take, instead of taking sum of squares, take sum of some other powers.
Some of, yes, sir.
Then raise it to the
Yes. So they called it, yes, there are higher power moments calculations. They called, I forget the term, but yes, there are. So P variations or something, so they can do these things. So there are literature, whole lot of literature, P variations or the terms.
Has there been any comparison of the normal geometric Brownian motion model in the fractional one?
As a model means a practical application?
Like the standard one that you have. You don't put the VH into the model. You can take this one, like the classic model.
Yes, classical model.
In which you don't have the fractional motion in it.
Well, okay, so this, you're talking about some numerical studies or, yes. So,
Like with the data to say which prediction.
Okay, yes, exactly. So exactly those kind of things are we are doing into. So we have actually tried to data one fractional Brownian motions, and that's like I am telling that not fixing that which model is better. So better to have some quantity to justify that, okay, if this, for this model this quantity is lower or that quantity is lower, so we have not fixed up with, but yes, that is actually the practical activity problem.
Other questions? If not, let's take an again.